Okay, so let's now implement the quantum variational classifier in Qiskit. So for this, let me share my screen, and you can download the notebooks that we are going to use from github.com/muf148 and go to Quantum Machine Learning with Qiskit 2.x and download this QML3A QVC Koi dataset file and the QML3B QVC leukemia file. Once you have downloaded this, actually, let me share just the VS Code instead of the whole screen. All right, so we let's first go through this QML3A notebook. And in this, I'm just implementing this model. And for this purpose, I'm creating a very simple data set. So the data set is has only one feature, and its value is from 0 to 2 pi. While generating the data set, I have already scaled it. You see, I'm generating data set from 0 to 2 pi, and there are 50 values in the data set. And then I'm assigning the labels arbitrarily. So it's a choice which is being assigned randomly. Some points are being assigned -1 and some points are being assigned 1. So in that respect, this is actually an extremely tough data set for classification purposes. You see, the minus and 1 data points are all mixed up together. And since there are 50 examples, it's really hard for any model to separate them. So, however, the data set itself is simple. And before we implement a model, what we can do is split it into uh, a test set and a train set. So for this purpose, you can just use train test split from the sklearn and prepare two data sets. And now you see I have a test size of 15 and a training size of 35. Now, once we have this data set, we need to prepare our model. And let me just start with a simple model. Actually, let me just run all this thing and let we can use a model that we were actually talking about in lecture 1 of this workshop. So let me just remove even the header marks and use this circuit. So just an a rotation around x-axis to encode x and a rotation around y-axis to encode theta. So theta is my trainable parameter and x is the input parameter. And from here, by using the circuit.parameters, I can see which one is coming first. So x is first coming before theta. So whenever I send data to this, x is my input parameter. And let's define z as my observable. And uh, with this observable, let's define a forward pass. So this is a function that compute the expectation values. So computation of expectation value is called a forward pass here. So it takes the circuit input parameters and weight parameters and the estimator and observable as input. Observable is just z, and estimator is the estimator that we want to use. For example, do we want to use a simulator? And whether that simulator is an air simulator or a state vector simulator, we pass it here. Or it is an IBM quantum computer or other quantum computer that comes in estimator. So input parameter is our x and weight parameter is our theta and circuit is circuit. And you see when the input comes here, I'm trying to zipping the parameters by combining the weights and the input parameters. And just since I have many input parameters, like there are 50 inputs and there's only one weight parameter, so I need to work out the expectation value for 50 circuits. Because for each input X, I need to compute the expectation value and then, in the my loss function, I'll be just adding them together. In the loss function, I'll use all of them to compute the predictions. So first I use just broadcast, this weight to an array. So if the weight is like one, I prepare an array of ones with 50 values. So it's just with input parameter as like it prepares a list which looks like input parameters, like it has the same shape, but it has values weight parameters. Anyway, so I prepare this primitive unified block of circuit, observable, and parameters. You can also optionally pass the tolerance in the expectation value here after the comma if you want. And then it says estimator run, and at the end I compute the expectation values. I extract them with .evs, and now this expectation value is a numpy array. It's a numpy array that contains 50 expectation values for each of the input x. So this is a forward pass function, and then this is a simple loss, which is a mean square loss. You can also use a binary cross entropy if you want. What it does, it uh, compute the difference of the predicted and the target value and take its square and then compute its mean, like add all of them together and divide by the total number. So this is the loss function. And then let's see how we are computing the cost. So with MSE loss weights, it takes the weight parameters as input and then pass this circuit and input parameter and all of this thing to predictions, which is a forward pass, the circuit over here to compute expectation value. So from the prediction, so what I'm doing is using the prediction directly as the predicted label, because my prediction is going to be between -1 and 1. So if the label is -1, and the minus value would be closer to that. If a label is +1, it would be closer to that. And then this target is just the target label that we have already arbitrarily assigned. And then I'm appending this cost to this objective function vals. And also in the every 10th iteration, I am printing the value of the loss and the iteration number. And it's returning the cost at the end. So once we have this, we can use, let's say, this minimize function from SciPy optimization package. And this takes as input the loss function, the weight parameters, the method for Kobila is a very popular method. You can use other stochastic methods as well. And then in options, I'm specifying that the maximum iterations are 100, and it will stop before 100 as well if the change in cost is less than 10 power minus 8, which means that it's not changing anymore. So there's no need to go ahead. And you see, I'm initializing the weight parameters randomly, and uh, I'm multiplying with 2 pi just, as a scaling parameter. So once we have this, and you see the target is the Y train, and the input parameter is the X train. So the X train is the X training set and Y train is the Y training set. So let's run it. And you see it quickly runs through. It's a simple circuit, and it stops even before 100 because the tolerance is reached. And then you can plot the cost, and you see the cost uh, is, small, becomes small very quickly. And then we can check the accuracy. For training accuracy, what I do is use this forward pass, give it circuit and the X training data, and this, res of X is actually this thing. So this RS is contain results, and in this result, X label refers to the parameters. Weight parameters are labeled X in this output. So from here, I'm taking the weight parameters and passing these trained weight parameters to the circuit. And from this prediction, you can print the prediction here. You can see I'm printing the actual label over here, and these are the predicted labels. So at many points, it predicts correctly, and at many points it predicts wrongly. And we have a simple interpretation function that if prediction is greater than 0, the expectation value greater than 0, assign it 1. If expectation value less than 0, assign it -1. And if we use this predicted interpretation function, we can see that the training accuracy is a modest 62%. And then you can check the test accuracy as well. So just provide the X test data here and the trained weights. And again, in the same way, these are the predicted and these are the actual labels in the test set, and the test accuracy is also about 60%. So with a very small circuit and with a very, very difficult data set, don't think that this is an easy data set just because there's only one data point, feature X, and 50 examples. So it's a very good, it's a very hard data set because the labels have been assigned randomly. So this is how we can implement this quantum variational circuit. Let me see if there are questions from people. So if not, let me ask, this question to all of you. How can we improve the accuracy based on what you have learned in the last 3 days? You can write in the webinar chat. Just say anything. Let's see. Good that some people are thinking. So let me, give a few pointers. In the first lecture, we saw that we can model more and more complex functions by repeating our layers. So one thing you can do is actually have repeats just this circuit, like uh, instead of go to this circuit. Okay, sorry, let me share the screen again. So one thing that we can do is just repeat this block. Okay, so because we saw in the first lecture that by repeating, we can get access to more complex models. Okay, so it means that we should be able to model with a better function or a more general function. So let's see if it does lead to a better accuracy or not. It has actually gotten worse. So let's increase it even more. That can sometime happens. Okay. So the test accuracy has increased. And one way is actually that let's say we don't change the input block and just repeat the, even though that wouldn't make any, much sense. Because by repeating Ry, we're essentially adding the angles. So instead of this, there's another possibility, and that is that let's make, instead of one, let's have two parameters. Okay. So suppose that instead of theta, we have two parameters. I will also have to put increase the number of weight parameters over here. Actually, let me go to a file that I have already prepared. So you see here in this case, I have two parameters. So with two parameters, you will have to make little bit of a change how the parameters are generated here, the initial parameters, and also how this function is combining the parameters, because you see now there are two weight parameters. So in creating this list of parameters to pass in the pub, I have added another parameter. So if you have like two parameter circuit, then the accuracy increases little bit to 62 here and 60 here. So by increasing the number of parameters, and then there's another way we can increase the accuracy, and that is that we can have the same data on multiple qubits. And in that case, to implement that, what you will have to do, you will have to have uh, more uh, Z, strings, a longer Z string in the observable. So by doing these things, you can try to improve the training and test accuracy of this circuit. And that's actually one part of the assignment that we have for you. So the first assignment is essentially just playing with this model, and either by increasing the repetition horizontally or vertically, or maybe by doing both, or introducing more parameters in the circuit, you are supposed to improve the accuracy as much as you can. And I think I have given a number of 90% that try to go to that accuracy. And you will see it's a little bit non-trivial problem to increase its accuracy to that level. Any question about this? If not, let me now explain its implementation for a second data set, which is a practical data set and a bit more involved. So for this, let's go to file 3B. Now, this is a data set that is used to classify this leukemia file, and it has 47 ALL sample and 25 AML sample. ALL and AML, they refers to like two types of leukemia, and each sample has thousands of features in it. So actually, it's uh, a subset of a gene expressions of a patient. So, but I'm not going to use all of them. What I did in this file, I only uploaded 12 of them. So you see that in this X file, I'm only keeping the first 12 features. And in exercise that you have to do, you have to keep 20 features. So you will select 1 to 21 features from this data file. So this is a 12 feature data set, and let's just see. So there are 72 total sample, and each sample has the X has 12 features in each example, and there are labels in Y. So these labels, you see, I have changed them to 1 and -1. So what I did that wherever there's ALL, I replaced it with -1, and where there's not ALL, it will automatically replace 1. There's a question in the chat. Looks like a logit survival test. Uh, I'm not sure if it is like that or not. It's actually an actual data set published about 26 years ago of actual patients. Okay, you notice one thing that I didn't do the scaling. So all of the data is actually here. So let's see how good we do without scaling. So I split it into 80% and 20%, and which means that my X is 57 and test has 15 samples. And just to give you a feel of what data look like, so the training data X is something like this. You see -3, -6, some number are 9. So the data is almost close to like 0 to 2 pi, but many numbers are outside of this range. So anyway, let's use this unscaled data, and I'm using this test size, train size, and number of samples that I will use later on. And let's just check. So you see the training size is 57, the test size is 15. Now, this is the part where the CN as engineer comes in, that what feature map you want to use for this. I have 12 features. So let's say I use ZZ feature map. So in ZZ feature map, I will need 12 qubits, because in ZZ feature map, the number of qubits and number of feature have to be the same. If you want to use efficient SU2, the number of qubits would be drastically reduced. If you have like one repetition, the features would be, I think, reduced to 1/4. And if you have like two repetition, you can reduce it even further. And if you use other feature maps, you will need other thing. And actually, I discovered this feature map for this data set after spending many days on this by trying many different feature maps. And at the end, I saw that this seems to be working the best so far. So I use this feature map, and then I also have to decide what circuit to use for the to encode my parameter. And for this, I actually had a hard time. I tried almost all of the feature maps that we studied in the class yesterday, and none of them were giving good results. So then I came up with this feature map, which you see, it's a simple one that's like 2 qubits and just CX, 2 qubit CX. And it's not like all qubits are not entangled, like these two are entangled, and then they are not entangled with the other ones. So it's a very simple map. And if I choose this map, and you see this has 24 trainable weights, I can actually have more. You can just repeat it again, and you can get maybe another 12. If you maybe you want to put CX here, CX here, CX here, and repeat it again. So this number of parameters actually is a very important thing. If you have many more parameters, your circuit is more likely to overfit. And so this also has to be chosen judicially. Anyway, so after this, I prepare a full circuit now like this using this dot compose method. So with dot compose, I can combine the feature map, and then I can put this ansatz onto this, add to this feature map. This ansatz is just this QNN circuit that I'm talking about, this one. So feature map was the circuit on top, and ansatz is this circuit. So we can combine both of them together. And once we combine, this is the circuit. And now after this, you see my observable is a string of Z operators, and it's multiplied with number of qubits. Whatever the number of qubit is, this string will, its length will increase. And after this, the forward pass is defined like this, where again, the weight parameters and input parameters are being combined using concatenate this time, not with the zip as I was doing in the other file. And at the end, we are getting expectation values. And the loss is still this mean square error loss. And then the mean square loss weights is, again, it's being done the same time, except that instead of printing every 10th iteration, I'm now printing every 50th iteration. You see things like this, that this nb dot array, this means simply that this weight parameter has to be an array, and the output is also supposed to be an array. This is like a higher level Python coding habit, that you just want to make sure that the different variables have proper data type. Now we are going to train, and again, let's say I'm setting 200 iterations, and I'm training for one epoch. And you see the initial weights they are being generated randomly and scaled to 2 pi. And if I run it, it's gonna take like 4 or 5 minutes. So that's why I have already run it. And you see, this is the convergence of the objective function, the cost. And I guess if I would have run it a little bit longer, it would have converged to an even better value. Okay. But with this, I was able to get a test accuracy of 84%, train accuracy, but the test accuracy was not that good. It's only 53%. And in this case, I made an error. And that's actually a very common error when you start working in quantum machine learning. And that error is this, that I didn't scale my data to be within 0 to 2 pi. And then I corrected it in another file. So let me do this. And in this, let me go back. So this is the same file, except that uh, I'm now rescaling the data from minus pi to pi simply by finding the minimum maximum and by x minus x min divided by x max minus x min and scaling it to be multiplying with 2 pi and then subtracting minus pi. So with minus pi subtraction, this becomes from minus pi to pi. If you don't do this, that's also okay. It would be scaled from 0 to 2 pi. Now with this rescaling and keeping everything exactly the same as before, we get a training accuracy of about 86%. And the test accuracy actually has worsened. It has gone down to 46, which means that my model is beginning to overfit. Okay, so it means I might have to reduce the number of parameters or maybe change to another model if I want to increase the test accuracy. You have been asked in the exercises to solve the same problem, and instead of keeping 12 features, you will have to keep 20 features, load from 1 to 21, and then come up with your own feature map and ansatz, and try to get a training and test accuracy that is more than 85% for both test and training set. So let me invite any questions. I'll upload this file with rescaled X to the GitHub also. Okay, so if there are not any questions, let's meet again tomorrow for quantum support vector machines.